Right now, while you're sitting there watching this, something 26,000 light years away is exploding. Not once, not twice. Over and over every single day, without stopping, without warning, and without any pattern anyone can predict. For 50 years, we told ourselves a comforting story about the black hole at the center of our own galaxy. We said it was calm, we said it was old and tired and mostly asleep. New telescope data has now torn that story apart, and the scientists who did the watching admit they are still struggling to explain what they found. Let's talk about what the center of the Milky Way actually looks like, now that we finally have the tools to watch it properly. For decades, the object known as Sagittarius A star had a quiet reputation. Compared to other supermassive black holes across the universe, ours looked almost boring. Take the giant sitting at the heart of the galaxy M87, roughly 53 million light years from here. That black hole is about 600 times heavier than ours, wrapped in a blazing accretion disk firing jets of plasma that stretch for thousands of light years. Next to a monster like that, our own galactic center looked starved, dim, and half asleep. That was the accepted picture for a long time, and honestly, the evidence seemed to back it up. Sagittarius A doesn't rip stars apart on a weekly basis. It doesn't glow anywhere near as bright as its cousins elsewhere in the universe. So when astronomers finally got the chance to stare at it for the longest, most detailed observation window in history, almost nobody expected to see what came back. Before we get into what was found, it helps to understand exactly what sits at the middle of our galaxy, because none of what follows makes sense without it. Sagittarius A is located about 26,000 light years from Earth, in the direction of the constellation that shares its name. Its mass is close to 4 million times the mass of our Sun, and all of that mass is packed into a region only around 15 million miles wide. To put that in perspective, that's roughly 1/6 of the distance between the Earth and the Sun. Imagine taking everything that orbits our star, every planet, every asteroid, every scrap of dust, then multiplying that mass by roughly 4 million, and squeezing the whole thing into a ball smaller than the orbit of the planet Mercury. That is the object sitting at the center of the galaxy you live in. What that kind of mass does to the space and time around it is genuinely hard to picture. Close to the black hole, time itself slows down compared to time out here where we are. A clock placed near the edge of Sagittarius A would run measurably slower than the clock on your wall. Light bends into strange arcs and loops as it passes close to the black hole, and objects sitting on the far side can have their light smeared around the edge of the event horizon like a ghostly reflection. That effect is exactly what showed up in the very first image of Sagittarius A, released in 2022. Light from the back of the glowing disk had been dragged almost all the way around the black hole before finally escaping toward our telescopes. The event horizon itself, the actual point of no return, sits about 7 million miles from the center of the object. Cross that line moving in any direction, and there is no way back. No light escapes, no matter escapes, no information escapes. We can never directly see the horizon because, by its very nature, nothing crosses it and comes back to tell us what's there. All we can ever observe is the behavior of everything trapped in orbit around it. Here's something worth sitting with for a second. Tonight, if you look toward the constellation Sagittarius, you are looking directly at this object. You can't see it with your eyes because of thick clouds of dust between us and the galactic center block almost all visible light from reaching Earth. But the radiation from its flares is arriving at this planet right now, light that left the black hole's surroundings long before recorded history began. We know just how violent the environment around Sagittarius A is because of the stars trapped in its orbit. One of them, a star astronomers call S2, loops around the black hole on a 16-year elliptical path, swinging as close as roughly 11 billion miles before flying back out into the darkness. At its closest approach, S2 is moving at more than 17 million miles per hour. A bullet fired from a rifle travels at roughly 800 miles per hour. That means S2, at its fastest, is moving close to 10,000 times faster than a bullet. And it isn't even the record holder. Other stars caught in the inner cluster around the black hole have been clocked at speeds above 8% of the speed of light. So how did we even figure out something invisible was sitting there in the first place? It started with radio waves. Back in the 1970s, astronomers picked up a strange, compact source of radio emission coming from the direction of the galactic core. By the 1990s, 2 separate research teams began tracking individual stars near that source, watching year after year as those stars whipped around something nobody could actually see. The math left no other explanation. To bend stars into orbits that tight and that fast, whatever sat at the center had to weigh about 4 million suns, all crushed into a region smaller than the orbit of Pluto. Nothing except a supermassive black hole could account for it. 2 of the scientists behind that discovery, Reinhard Genzel and Andrea Ghez, were awarded the Nobel Prize in Physics in 2020. They never saw the black hole directly. They proved it existed by carefully watching what it did to everything nearby. Then, in May 2022, after literally decades of effort, the Event Horizon Telescope team released the first ever direct image of Sagittarius A. It looked like a glowing orange ring wrapped around a dark center, gas heated to millions of degrees lighting up the ring while the shadow of the event horizon sat black in the middle. To understand how difficult that photograph actually was to take, imagine standing in one city and trying to photograph a single donut resting on the surface of the moon. That's roughly the tiny angular size of Sagittarius A as seen from Earth. The team pulled it off by linking radio dishes scattered across multiple continents into one giant virtual telescope, effectively turning the whole planet into a single lens. Data from the South Pole station was so massive, it had to be physically flown out on hard drives rather than sent over the internet. It then took roughly 5 years of computer processing to turn that raw information into one final image. That image was an incredible achievement. It was also just a single frozen frame, a snapshot of something that, it turns out, never actually holds still. To see what Sagittarius A really does, you would need a telescope capable of staring at it continuously, in a type of light that can cut through the dust with enough sharpness to track activity happening inside the glowing disk in real time. There was really only one instrument capable of doing that job. The James Webb Space Telescope launched on Christmas Day 2021. It orbits the Sun about 1 million miles from Earth, sitting at a stable point in space called L2, cold enough to keep its huge mirrors sharp in infrared light. Infrared is exactly the kind of light that slices through the dust hiding the galactic center, which means Webb, more than any telescope built before it, could finally look straight at something that had been hidden from human eyes for the entire span of our species' existence. An astrophysicist named Farhad Yousefzadeh, working out of Northwestern University, led a team that used Webb's near-infrared camera across 2023 and 2024 to attempt something nobody had ever tried before. They pointed the telescope at Sagittarius A for a combined total of 48 hours, split into stretches of roughly 8 to 10 hours, spread out over the course of a year. Their goal was almost embarrassingly simple. Just watch. Don't blink. See what the galaxy's central black hole actually does when nothing forces it to hide. From the very first observing session, the black hole was doing something the team didn't expect. The glowing ring of superheated gas circling the black hole, the accretion disk, was flickering constantly. There were no calm stretches, no predictable rhythm, just restless, continuous brightness the entire time the telescope was watching. Yousefzadeh later described the activity as constant bubbling, never settling into anything resembling a steady state. On average, the disk produced 5 to 6 major flares every single day. Between those larger bursts, smaller flickers came and went in a matter of seconds, and some of the faintest flickers, barely above the background noise, seemed to smolder quietly for months at a time. Every observing run, the team saw something new, different patterns, different brightness levels, different mixes of bright flashes and dim glow. In interviews, Yousefzadeh admitted the team had expected occasional flares because that's normal for supermassive black holes. What they had not expected was that there would never be a quiet moment at all. Sagittarius A, it turns out, doesn't really produce individual flares in the way we imagined. It's closer to the truth to say the entire disk is one continuous flare, and what we call flares are really just the brightest peaks inside a storm that never actually stops. Picture it like this. A dim ember glowing faintly in the center of the frame, surrounded by a soft haze of light. Every few minutes, somewhere inside that haze, a hot spot suddenly brightens, then fades back down. Sometimes a bigger pulse rises out of the background glow, holds for several minutes, then collapses again. Sometimes a small flicker just sits there steady for an entire observing session, refusing to fade or grow. Compress 9 hours of that footage into a 30-second clip, something the research team has actually done and released publicly, and the result looks unsettlingly alive. It doesn't look like a stable gravitational anchor sitting quietly at the middle of the galaxy. It looks like something breathing. Nobody could find a pattern in any of it, not on the scale of seconds, not on the scale of hours. The bursts happened whenever they happened, wherever they happened, at whatever brightness they happened to reach. And from a physics standpoint, that randomness is itself meaningful. If the chaos isn't running on some clean, repeating cycle, like a wobble or a tidal rhythm, then something more complicated is driving it from deep inside the disk. Here's where the story gets even more interesting, because the last 2 years have added pieces to this puzzle that weren't part of the picture before. In April 2024, a separate research team used a different instrument on Webb, the mid-infrared instrument known as MIRI, and captured something nobody had ever recorded before, a full flare from Sagittarius A in mid-infrared light. That particular slice of the light spectrum is invisible from the ground because Earth's own atmosphere absorbs it almost completely. The only way to see mid-infrared light coming from 26,000 light-years away is from space. That morning, Webb recorded a roughly 40-minute outburst tearing through the disk. A team led by Sebastiano von Fellenberg at the Max Planck Institute for Radio Astronomy in Germany modeled the event and found the cleanest evidence yet for a process called magnetic reconnection. Inside the accretion disk, magnetic field lines get twisted and tangled as plasma spirals inward. When the tension builds past a certain point, the field lines snap apart, releasing a massive burst of energy and flinging charged particles outward at speeds close to the speed of light. Then, in 2026, a completely different instrument added another twist. Astronomers using the ALMA radio observatory in Chile found clear evidence that Sagittarius A is blowing out a steady wind, a stream of material pushed away from the black hole rather than falling into it. That's a discovery scientists had been searching for, in one form or another, for over 50 years. Around the same time, a separate group working with the Chandra X-ray Observatory confirmed that this same hot outflow has been quietly shaping the surrounding gas for a long time. And in the most surprising addition of all, data gathered by the newer X-RISM Space Telescope suggests that sometime within roughly the last few hundred to 1,000 years, Sagittarius A actually flared far more dramatically than anything ever recorded in modern observations, based on X-ray light still echoing off nearby clouds of gas. In other words, the version of the black hole we're watching today, restless and constantly flickering, might actually be the calm phase compared to what it was doing a few centuries ago. Put all of that together, and you get a very different picture of our galactic center than the one most of us grew up with. It isn't just flickering randomly for no reason. It's blowing wind outward, snapping magnetic fields apart, echoing with the aftermath of a much larger outburst from the recent past, and doing all of it constantly, whether or not anyone happens to be watching. The wind discovery deserves a little more attention because of how long scientists had been chasing it. For half a century, researchers suspected that black holes like ours had to be pushing some material away, even while pulling other material in, simply because the numbers never quite balanced without it. Gas falls toward the black hole from every direction, but only a small fraction of it actually crosses the event horizon. The rest has to go somewhere. The 2026 findings from the ALMA array finally gave scientists a direct look at that missing piece, a steady outward wind carrying material away from the black hole's immediate surroundings. Around the same time, Chandra's long-term X-ray monitoring lined up with that picture, showing a hot outflow that appears to have been quietly reshaping the gas near the galactic center for a very long time. Instead of a black hole passively waiting for material to fall in, the new picture is closer to something constantly pushing and pulling at once, inhaling and exhaling in the same breath. Then there's the X-RISM result, which might be the strangest piece of all. By studying how X-ray light bounces and echoes off nearby clouds of gas, scientists were able to work backward and estimate that Sagittarius A produced a major outburst sometime within roughly the last few hundred to 1,000 years, a flare far larger than anything caught by modern instruments. Clouds of gas near the galactic center absorb radiation from an event like that, and then slowly re-emit it over centuries, acting almost like a delayed echo chamber. Reading that echo lets astronomers reconstruct outbursts that happened long before any telescope on Earth existed. If that finding holds up, it means the constant flickering Webb has been recording over the last 2 years, as dramatic as it looks, may actually be Sagittarius A on one of its calmer stretches. Whatever happened a few centuries ago was, by comparison, on another scale entirely. One particular measurement from the original 48-hour Webb campaign turned out to matter more than almost anything else in the entire dataset. Yusuf Zadeh's team observed the black hole simultaneously at 2 different infrared wavelengths, one at 2.1 microns and one at 4.8 microns. Every time a flare occurred, the shorter wavelength brightened first. The longer wavelength always followed behind, lagging by anywhere from a few seconds up to about 40 seconds. That delay might sound like a minor technical detail, but it's actually the most important single measurement in the whole dataset. It works like a fingerprint. Shorter wavelengths come from particles carrying more energy. As those particles lose energy over time, they start emitting light at longer and longer wavelengths. Watching a flare shift from short wavelength to long wavelength is like watching, almost in real time, a group of particles that had just been violently accelerated to near light speed gradually cool down and lose that energy. Scientists call this process synchrotron cooling, and before Webb, nobody had ever directly measured it happening around our own galaxy's black hole. What that actually means is almost hard to wrap your head around. We are watching, close to real time, particles being flung outward from the edge of a region where the normal rules of physics start behaving strangely. Some of those flares point in random directions through space. A small number, purely by statistics, must be pointed roughly toward Earth. At a distance of 26,000 light-years, that radiation is far too diluted to pose any danger to us. But every time you watch footage of Sagittarius A flaring, a fraction of that light is energy generated at the boundary of a black hole. Energy that has been traveling through the emptiness between the stars for 26,000 years, only just now landing in the mirrors of a telescope parked 1,000,000 miles from Earth. We are not looking at ancient history in the abstract sense. We are looking at events that were unfolding at the center of our galaxy, while early humans were painting on the walls of caves. Here's the part of this story that probably deserves more attention than it usually gets. Sagittarius A is not the most violent supermassive black hole out there, not even close. By almost every objective measurement, it ranks among the quieter ones. The black hole inside M87 is 1,600 times heavier, wrapped in a denser disk, and regularly launches plasma jets that stretch thousands of light years into space. Elsewhere in the universe, there are quasars powered by central black holes so bright they outshine their entire host galaxies combined. Compared to monsters like those, our own galactic center looks practically asleep. And that's exactly what makes the new data unsettling. Even the boring one, the black hole we spent decades dismissing as calm and uneventful, has an accretion disk that never actually settles down, blows outward wind, snaps magnetic fields apart in bursts of violent energy, and shows fingerprints of a much bigger outburst sometime in the last 1,000 years. On average, something 15 million miles across is exploding brightly enough to be detected across 26,000 light years of dust roughly 6 times a day. It has been doing this for billions of years, completely unnoticed, completely unrecorded, until the last couple of years finally gave us the right tools to watch. There's still a major piece of this puzzle scientists haven't solved. Based on current models, the amount of gas actually falling into Sagittarius A isn't enough to account for the level of activity Webb is recording. Something appears to be feeding the disk more steadily or more violently than the existing models predict. Maybe it's a stream of stellar wind coming from stars in the surrounding cluster. Maybe it's a slow, ongoing tidal disruption that nobody has properly accounted for yet, or some combination of the newly discovered outflow and older, unseen sources of material. Yusuf Zadeh's team is now hoping to secure a full 24 uninterrupted hours of observation time to hunt for finer structure hidden inside all that chaos. In a very real sense, the science is still racing to catch up with what the telescopes have already shown us. Take a moment and actually picture what's sitting at the center of the galaxy you live in, a region about 15 million miles wide, holding the crushed mass of 4 million suns, an event horizon with a radius of roughly 7 million miles, a disk of plasma heated to millions of degrees, spinning at speeds close to the speed of light, being torn apart over and over by its own tangled magnetic fields, throwing bursts of high-energy radiation outward in every direction hour after hour. Stars nearby being slung around at a meaningful fraction of light speed. And every single star in the Milky Way, including the one lighting your sky right now, locked into one enormous, slow orbit around that same chaotic point. Our sun takes roughly 230 million years to complete a single lap around Sagittarius A. Since Earth first formed, we've made only about 20 of those laps. There is something genuinely humbling about realizing the object holding your entire galaxy together isn't the stable, quiet anchor we were taught to picture in school. We grew up imagining the Milky Way as a giant spinning wheel of stars, held and shaped by one simple silent mass sitting at the very center. The newest observations make it clear that anchor is anything but silent. It's a 4 million solar mass storm of restless, tangled physics, sitting right at the gravitational heart of roughly 200 billion stars, still doing things scientists who study it for a living can't fully explain. We tend to imagine black holes as things that belong in movies, or as strange curiosities sitting in some distant galaxy far removed from anything that touches our lives. But the one holding our own galaxy together, the one keeping every star in the Milky Way, including our own sun locked in its slow orbit, is right now, while you're watching this, throwing bursts of radiation out into the darkness. It was doing exactly this while the pyramids were being built. It was doing this while the first humans were walking across Africa for the very first time. And it will still be doing this long after everyone watching this video today is gone. 26,000 light years away, in a place we will never physically reach. The center of the Milky Way keeps pulsing with light that we have only just learned how to see, and every one of us is slowly spiraling around it, along with everything else in this galaxy. Thanks for watching, and I'll see you in the next one.